So section 15.3, partial derivatives. So we move on through the calculus. Well, now we did a little bit of functions of the algebra domains of multivariable functions. Then we moved on to the limits, and well, what's the next topic after limits? Derivatives. Well, the rules for differentiation that we're going to use are, well, nothing new except that we're adding more variables and new notation. So when we found derivatives for single variable function, we use the notation dy dx, or df for the function f, dx f prime of x, y prime. All right. So those were the different notations that we use here. Well, so we're going to use a different symbol here for partial derivatives. And it's a curly D, that's to denote partial derivative. And and this symbol is called, it's usually or more often called Jacobi's D. It's not a straight D, it's curly. That's to denote partial derivatives, and it's named Jacobi's D after the mathematician who used it the most. Well, there's like a debate who he was not the first one to use it. There were other two mathematicians using this symbol before, but then they stopped using it. But this guy reintroduced it again, so that's why the name of the symbol is really after him, because he was the one who reintroduced it. All right. And well, so how do we find partial derivatives? Well, partial differentiation is the same process of finding derivatives with respect to one independent variable, but in this case we are going to hold the other variable, or the other variables, we're going to hold them constant. I think a few examples will be better in this case, right? So before, let's look at the notation. When we want to find the partial derivative with respect x, let's use partial z with respect x, partial f with respect x, or sometimes for short, the function z with this subscript x right here. This subscript x, this one should have been an x here, and yeah, those are our y's. These subscripts denote that we are differentiating the function with respect x, and likewise we're denoting that we're differentiating with respect y. So let's have a look at some examples. Find both partial with respect x and partial with respect y for this given function. Z equals f of x y equals 3x minus x squared y squared plus x cubed plus times y. All right. So it's like writing the number 2, but without the symbol. It's like writing number 2 without going all the way. So just like this. dz with respect x. Well, so we're going to differentiate all the x's. So number 1, what's the derivative of 3x? 3 minus, okay, be careful, because in this case, since we are differentiating with respect x, everything else will remain constant. So in this case, we are differentiating x squared times a constant, so we really differentiate the 2x y squared. In just the same way that if we were differentiating like we differentiating 3x, that's a constant times x. So we differentiate the x and we keep constant everything else. Plus the derivative of 2x cubed y, well in this case with respect x, that's 6x squared simply times y. Alright, so that's the partial derivative with respect x. Let's do the partial derivative with respect y. Okay, we take the derivative with respect y, we hold everything else in terms of x in this case, remaining constant. Okay, so what's the derivative of 3x? So in this case 3x is constant. What's the derivative of a constant? 0, right? Because we're differentiating with respect y, rather x is constant. So this is 0. Now, what's the derivative of y squared? 2y x squared. All right, x squared is just a multiple constant in this case. Let me write it in alphabetic order. And well, plus the derivative of 2x cubed y, but in this case we're differentiating y, everything else is constant. 2x cubed is just a number, it's just a constant. But what's the derivative of y? 1 times 2x cubed, that's simply 2x cubed. Alright. We're going to do more examples. So what did we do here? Hold y constant, hold x constant. Alright, let's look at the next example. Let's find both partial derivatives for the function z equals f of x equals to x equal x times e to the x squared y. Alright, so let's have a look. So the partial derivative of the function z with respect x, well, in this case we are going to hold the y to be constant, in this case y. So check this out. If we focus on this function, notice we have a product of the function. That means we will have to use the product rule. Alright, so for the product rule, let me write down the formula. So the derivative of a product uv prime, that's u prime v plus v prime u. Okay. Well, in this case, since we're differentiating x with respect to x, so the derivative of x, which is 1 times v, which is the exponential e to the x squared y, plus the derivative of the exponential with respect to x, and careful here. So the derivative of the exponential, again, is always itself, e to the x squared y, times, by mini chain rule, the derivative of x squared y with respect to x. But in this case, y is just a constant. What's the derivative of x squared in this case? So times 2x y. Alright, we're bringing that constant multiplying x squared. Alright, so that's the derivative of v times u, which in this case is x. So let's simplify this derivative. So that's simply e to the x squared y plus 2x squared y e to the x squared y. So that's the partial derivative with respect to x. Let's look at the second partial, or the partial with respect to y. So, in this case, pretty much everything is remaining constant. Well, x is constant, so we are essentially differentiating e to the constant times y. What's the derivative of that? Well, it's going to be exactly the same. X e to the x squared y. Now, what's the derivative of x squared y with respect to y? Careful here. X squared only, right? Because that's the multiple constant, the constant multiplying y. The derivative of y is just 1. 1 times the constant x squared is x squared. Simplifying this, that's x cubed e to the x squared y, and that's the final answer. So yes, I hear it. At the beginning it's kind of weird how we hold, variables constant. That's because we're taking a derivative with respect to one variable and then a derivative with the other variable. One variable is changing, the other is not. Well, for example, when we take the partial derivative with respect to x is changing, y is not. When we are taking the derivative with respect to y y is changing, x is not. And well, they're asking us to evaluate this at the point 1 comma ln of 2. Well, so number 1, dz over dx bar, this bar is to denote that we're going to evaluate at the order pair 1 comma ln of 2. So this will be, for the first partial derivative, e to the ln of 2 quantity, e to the 1 squared ln of 2 plus 2 times x, which is 1 squared, y ln of 2 e to the 1 squared ln of 2. Okay, so let's simplify this. So, okay, 1 squared, that's going to be 1. Do we agree with that? So that's going to leave us with e to the ln of 2. But in this case, the e and the ln cancel out. Same over here, e and ln cancel out. And well, this will be simply 2 plus 2 times 1 squared, which is 2, ln of 2, and times 2. But be careful when multiplying this number. These two will be multiplying the 2 in front of the ln, not the 2 inside of the logarithmic function. That's the argument of the function, not it doesn't multiply with the outside. This will be 2 plus 4 ln of 2. And for the second, the last one, so the z over the y evaluated at the point 1 comma ln of 2, that equals to, well, x, which equals to 1 cubed e to the 1 squared ln of 2. But what's 1 cubed? Isn't it just 1? Mm-hmm. And again, 1 squared, that's just 1, and that's going to leave us with e to the ln of 2, which again can be cancelled out. All right, and this will be simply 2. All right. Okay, let's look at the geometric interpretation of this. All right, so which is hopefully what would help us get out of the weirdness here. You know, like holding one of the variables constant while the other is changing. So we have the surface here, and well, so it's the same concept as back in calculus 1 when we found the derivative. The derivative, it's the slope of the tangent line at a given point. As long as, of course, as the function is differentiable at that point, you know, all those conditions, it's continuous, all that. So, when we find the derivative with respect x, all right? So, that means we're seeing, in this case, we're having a slope in this direction, right? While, and in this case, only x is changing, but y is remaining constant. In this case, when we find the derivative with respect to y, we have a slope essentially in the y direction. Well, we don't call it m, you know, that's in single variable function. So it's just the partial derivative, that's the slope. All right? And notice the direction of the slope is in the y direction, and this slope is going in the x direction. All right, so that's the geometric representation. We have a surface. We're finding the steepness at a point on the surface in the same way that we found the steepness at a point on a curve in functions of single variable. Alright, so let's see. Let's find the slopes in the x and y directions, which is essentially what we did here. So we took a couple of partial derivatives, the derivative with respect x and the derivative with respect y, and then we evaluated at the point, and essentially this value is the slope in the x direction, and this is the slope in the y direction. Alright? Okay, let's keep practicing with partial derivatives. Find the slopes and the slopes in the x and y direction for the surface given by f of x equals to sine squared of x minus 3y. Then evaluate both at the point pi over 3, pi over 6, 1/4. All right. So I would rewrite this function to make it easier to understand about what we're going to do. So that's a sine x minus 3y quantity squared. So which rules do you think we should use to differentiate this function? Chain rule is one. Anything else besides chain rule? Well, I think that's pretty much chain rule, right? And there's like two, there's one, two, that's actually a three-layered function right here, right? So the partial, let me actually change the notation this time. So I'm going to say f subscript x, xy. That's to say the subscript x is to denote that we're differentiating with respect x. Well, so number one, so we're going to use chain rule, that's 2 times sine x minus 3y times the partial derivative of x minus 3y. Well, what's the derivative of x? 1. And because in this case we're holding y is constant, what's the derivative of negative 3y? 0. So just 1, right?
Aren't you missing the cosine?
Yes, that's what I meant to write, cosine. Oh no, not yet. That's the next in the chain rule. So what we did here is to differentiate the outermost layer of the function, like I have here, right? So we are differentiating. I will never regret buying this. Thank you. So we're differentiating something squared, all right? Which is 2 times the something to the 2 minus 1, okay, the inside. So we're going to differentiate the sine, which in this case is, oh, never mind, I did a mistake as well here. So the derivative of sine, that's cosine, all right, of x minus 3y. We're done with that cosine. The next one is to differentiate the x minus 3y with respect x, and this one is 1. All right. Let's just clean up parentheses and the like, So that's actually 2 times sine x minus 3y cosine x minus 3y. And no need to write that one. And I mean, you don't have to do the following. If you think of the trigonometric identity, did you notice one of the trigonometric identities? This is 2 sine cosine, which is actually 2 sine 2 times the double angle formula for sine. But again, you don't have to write this one like this. That's fine. We can just go with the other one, with the original one. That's fine. So let's see. What about the partial derivative with respect y? So the partial derivative with respect to y, that's f with a y in the subscript to denote that we're differentiating with respect to y. So the same. Again, we're going to differentiate the outermost layer, which is the something squared, right? So that's 2 sine x minus 3y to the first. All right, we're done with the power 2. Let's look at the next layer. For the next layer, what do we have? To differentiate sine, and again it's cosine. And the third layer, the inner one, is to differentiate. Be careful this time because we're differentiating with respect to y, right? So what would be the derivative with respect to y? Negative 3. X is held constant. That derivative is going to be 0. Let's simplify this. This will be 6, rather negative 6, sine x minus 3y cosine x minus 3y. All right. Okay, so they're asking us to find the slopes at the given point. At the point pi over 3, pi over 6, 1/4. All right, so let's evaluate those slopes. That is, we're going to evaluate f, that's actually, f subscript x at the point where x equals pi over 3, comma, pi over 6. So whatever we see the x, we're going to replace with pi over 3, and whatever we see y, we're going to plug in pi over 6.
What about the 1/4? Is that like the value for z?
That's a value for the original function. That's a good question. This is the z value for, if we plugged in pi over 3 and pi over 6 on the original function, that'll give us 1/4. But when it comes to, notice that when it comes to evaluating those slopes, all we need is the x and the y. So, what's next? Yes. So 2 times sine of x, which is pi over 3, minus 3 times pi over 6 cosine pi over 3 minus 3 pi over 6, and that equals to 2 sine. Okay, so pi over, or 3 pi over 6, isn't that a pi over 2? Okay, let me do the calculation. On the side, pi over 3 minus pi over 2. Oh, we need a 3 and we need a 2. So 2 pi minus 3 pi, that's a negative pi over 6. All right? So negative pi over 6. Negative pi over 6 cosine negative pi over 6. And well, you might not want to deal with negative angles. In this case, instead, how about use the even and odd properties of trigonometric functions? So recall that sine is an odd function. If you have a negative angle, that negative sign goes outside. However, the cosine function is an even function, and in this case, cosine of a negative number of a negative angle remains, remains positive. It's what we usually call the spit and swallow, if you will. So the sign, which is the odd one, spits the negative sign while the cosine swallows it, right? So that's another way to look at even and odd functions. So let's simplify the sign. That's going to be a negative 2 sine pi over 6 cosine pi over 6. So that's negative 2. Let me go here. Negative 2 times sine of pi over 6, which is 1/2. Is that a 1/2? And cosine of pi over 6, that's root of 3 over 2. And so that's cancel. Negative root of 3 over 2. So that's the slope in the x direction for the surface given by the function f of xy, or z equals to sine squared of x minus 3y. Now let's look at the stiffness or the slope f subscript y at pi over 3 comma pi over 6. So I'm going to go a little faster here. 2 sine pi over 3 minus 3 pi over 6, which is also pi over 2, cosine pi over 3 minus pi over 2. And again, that's 2 sine. What we got for this, negative pi over 6. Well, it's actually negative 6 in the front, right? Mm-hmm. Negative 6. So negative pi over 6 cosine negative pi over 6, and that's a, oh, again, oh, come on, yes, so that's negative 6. Oh, actually this negative of the oddness of sine goes outside to multiply with a minus. See what I'm saying here? That's going to become positive sine pi over 6 cosine pi over 6, and that's a 6 times, okay, 6 sine pi over 6, that's again a 1/2, and root of 3 over 2, and 6 over 2, that's 3. That's going to give us 3 root of 3 over 2. That's our final answer. Those are the two slopes in the x direction and the y direction respectively. Alright? Let's practice a bit more. Let's do another example. Alright. So, partial f with respect x equals to, okay, the derivative of 1 is 0, and then minus the derivative of x minus 1 squared, that's 2x minus 1. To the first, no need to write to the first. The derivative of x minus 1, we don't need to write it because it's just 1. The derivative of f with respect y equals negative 2 times y minus 1. Alright, so we have the derivatives. Let's evaluate this at the given points. So, evaluate this when 2, you have the
y minus 2, for example.
y minus 2.
Yeah, it is. Yeah.
2y. Oh, it doesn't have. Wait a minute. What did I do wrong?
It's just that this is 2 with the on the original.
Uh huh.
It's y minus 2. And you copy the y minus 1 on the. You differentiated it.
Oh, it's y. Yeah, y minus 2. That's true. That's true. Never mind. Y minus 2. Thank you. So df dx at the point 1, 2, 1. Well, all we need is to plug in the x's and the y's. So that's negative 2 times 1 minus 1, which equals to 0. And on the other hand, the partial evaluated at y at the point 1, 2, 1. That's a negative 2, 2 minus 2, and it's also 0. Well, what does this result mean? So when we have this point and the partial derivatives get evaluated at that point and we get 0. So what happens when you evaluate a value on a derivative of a function in Calc 1 and you get a 0? There's no slope. The slope is 0. That is correct. That means at that point the surface is the point is flat. The surface is flat. Now, in the vocabulary, this means that 1, 2, 1 is a critical point in which at this critical point we may get a max or a min. And something new that we're going to learn in this class, not just maximum and minimum points, rather. We're going to learn about saddle points, and we already discussed a little bit about this when we were looking at these quadric surfaces. When we have this weird hyperbolic paraboloid that had at this point a minimum and a maximum at the same time, those are called the saddle points. So we're going to learn about this later in this chapter. Right, so in the meantime, let's call this just a critical point, or a point where the slope is equals to 0. Let's look at the next one. Find the slopes in the x and y directions for the surface given by f of x y equals to x squared over 3y plus 4y squared over x cubed. And then evaluate both at the point 6, negative 1, negative 674 over 54. I know the number looks ugly, but we're not even going to use it. That's just the point that belongs on the surface. Ultimately, because we're evaluating the partial derivatives with respect to x and y, we will just use the x and the y. All right. It would be, number one, convenient to rewrite this function. We cannot differentiate this function the way it is. It's not ready yet. Then how about 1/3 x squared y to the negative 1 plus 4y squared x to the negative 3. Right? So let's take the partial derivatives. So f subscript x, I'm going to go back to the f notation. And well, the derivative of this function with respect x, we're holding y constant. That's 2/3 x to the first power y to the negative 1. And the derivative of the second term with respect x, this is going to be negative 3 times 4, that's a negative 12, x to the negative 4, because we subtract 1 to the exponent, negative 3 minus 1 is negative 4, times y squared. How about we rewrite this nicely with positive powers? So that's 2x over 3y, and that's a minus 12y squared over x to the 4th. So that's the first partial derivative with respect x. Let's find the partial derivative with respect y. And then with respect y, the derivative in this case of y to the negative 1, holding x constant, well, that's negative 1. Okay, let me write this negative 1 explicitly. Negative 1 times 1/3 x squared y to the negative 2. Because we're subtracting 1 to the exponent, that's the general power rule. And the partial derivative with respect x for the second term, that's y squared. Okay, so that's going to be 2 times 4, which is 8. 8y x to the negative 3. This means, okay, let's write it down in a nicer form with positive exponents. So that's going to be negative x squared over 3y squared plus 8y over x cubed. So far, so good? All right.
In the beginning, what is that? Like a negative 1?
Which one?
The second derivative for y, the first number after the equal sign.
After this one? Oh, yes. This one, it's so I wrote it explicitly because
okay.
it's just to do the general power rule. So the power negative 1 multiplying the 1/3. So I didn't want to just write negative. So just so you can see where that negative 1/3 was coming from. So let's evaluate f sub x at x equals to 6 comma negative 1. So negative x, okay, so that's a 6 squared over 3 times 1 squared plus, oh, wait a minute, I think I'm mixing and matching here. Okay, so no, that's 2 times x, which is 6, over 3 times y, which is negative 1, minus 12 y squared, which is negative 1 squared, over x to the 4th power, in this case 6 to the 4th power. That's going to be a big number. All right, so that's going to be 2 times 6, which is 12, over 3. Is that a negative? Times negative in the front, that's oh, wait a minute, that's not negative. No, I was looking at both functions at the same time. So that's 4. And then minus, okay, 6 to the 4, that's 36.
Would it be negative 4 for that one?
Negative 4, oh, that's a negative. Yeah, now that we have this negative. And 12 over big number, 6 to the 4, what's that?
Was it 6 cubed?
Cubed? Oh, no, it's to the 4th, this one. The cube is for the partial derivative with respect to what?
What was the first one? Well, 96.
It's 296? 196?
1296.
1296. Oh, big number. And 12 over that number. So final answer, this should be 4 or negative 433 over 108.
Does that end up being positive on the right side? Negative 1. times -1 is positive. Times
This one?
Yeah.
So negative squared is, oh, that's a plus,
Is it
yes.
squared or cubed?
It's,
Squared.
that's squared. It's the square right here.
Wait, no, so it is negative.
should be negative.
Yeah, it was negative. Sorry, my bad. I thought it
Which
was
one?
cubed.
Oh, this,
You were right.
okay. Yeah, this one, yeah, that becomes, oh, that becomes negative,
You
yeah.
had it right. Sorry.
Yeah, negative. Yes. And we get negative 433 over 108. After using the what's it called? The frac command on your calculator. Let's evaluate. So negative, okay, x, which is 6 squared, over 3 times -1 squared, plus 8, y, which is -1, over x cubed, so that's a 6 cubed. Oh, another cute number here. So that's 36 over 3, isn't that a 12? -12. And plus 8 over 6 to the third power, big number. What's that big number?
216.
216, right? And after simplifying this, we should get -325 over 27.
I think it's -8 over.
Oh my God, I messed it up again. Yes.
So, do you want our answers to be in fractions, or can you like?
No, in fractions. So, well, it depends, preferably fractions. So, all we need to do, okay, let me open the graphing calculator. Okay, how do I go? So, -12 minus, is that 8 over 216? And well, we're gonna get this decimal, so then you want to go on your graphing calculator, math, and the very first option is actually highlighted, is the frac. Click enter and click enter again, and that's gonna give you your number in exact form. Of course, if you're working with pi, roots of 3, you know, those irrational numbers, we're not gonna get a fraction because those are irrationals. All right, so all right, let's see. Whoops. So that was our final answer. So let's extend these partial derivatives to functions of 3 or even more variables. So if we have a function w that depends on x, y, and z, well, to take the partial derivative with respect to x, what do? Hold y and z constant. If we want to compute the derivative, the partial derivative with respect to y, we hold x and z constants. And if we want the partial derivative with respect to z, we hold x and y constants. And we differentiate using the same, differentiation rules. Okay, so for this function, f of x, y, z equals xy plus y, z squared plus xz. Let's find, notice in this case, they're only asking us for the partial derivative with respect to z, not the remaining two. All right? So the partial derivative with respect to z, everything else is constant. So in this case, so partial f with respect z, so the derivative with respect to z for the first term, 0. What about yz squared?
2yz.
2yz. And then just x. All right. Is it making more sense now? At the beginning it was kind of weird, right? Like, wait, it's letter, it's a variable, but we're holding one of them or two of them constant this time. Example number 7. Find the partial derivative of the function f with respect to w. What do we have? F of x, y, z, w equals x plus y plus z divided by w. Number 1, it would be convenient to rewrite the function as x plus y plus z times w to the -1. Well, this madness multiplying the w to the -1 is just a multiple constant. Do we agree? because that's x, y, and z, and we want the derivative with respect to w. So the derivative of w to the negative 1 is, or rather, let me just, that's just negative 1 times x plus y plus z, w to the negative 2. And that's all. The remaining is just write it nicely. Negative 1 over, oh no, not 1 actually. That's x plus y plus z over w squared. Right? Same differentiation rules. What makes it weird maybe is the fact that we have a lot of letters going on. All we have to do is just keep in mind the variable that we're finding, for which we're finding the derivative of. Alright? So we have another one. Yes, we have another one. The derivative with respect z only for the function z sine x y squared plus 2z. Alright? Which differentiation rules should we use in this case? Product rule, right? Because in this case we have a product of the functions, yes, but in this case both factors rather contain the z. If the question were to find the partial derivative with respect x, would we need the product rule here?
No.
No. Alright? Okay, let's use the product rule on this one. So partial f with respect z. So that's okay, the derivative of z, which is 1 times sine x y squared plus 2z, and then by mini chain rule, the derivative of the quantity inside of the cosine function. Oh wait, no, that's it. No, what am I doing? No, I was going ahead. No, that's the next step, right? To differentiate the second factor, sine, that's cosine of the angle xy squared plus 2z times the derivative of the quantity inside, which is 2, and well, that times the x function, that's a z. So all we need to do here is just clean up the parentheses and write this product in a nicer way. Sine x y squared plus 2z plus 2z cosine x y squared plus 2z.
Where did you get that last z from?
From the product rule, let me write it again. So that's u v prime, that's u prime v plus v prime u. So this is u prime, this whole thing is v, and then this is up to here. This is v prime, and this is u.
Oh.
Yep. So it's the derivative of the first factor times the second factor without differentiating, plus the derivative of the second factor times the first factor without differentiating. Right? Okay, what's next? Higher order partial derivatives. And just the same way we found the first derivative of a function in single variable calculus, well, we can find a second derivative, a third derivative, a fourth, fifth, etc. As many derivatives as you want. Now, we need to be very careful with the notation for partial derivatives, repeated iterations of partial derivatives. Okay, back in calculus 1, so we went from f prime to f double prime. Right, that was one way to denote, or y double prime, or d squared over, or y dx squared. Now, let's pay special attention to this notation. Essentially, what we did from here is to find the first derivative and then differentiate this whole function with respect x. That is, we did this number 1, and we did this number 2. All right? And this is important because check the notation for the second partial derivatives. So, if we use the Jacobian notation, that is the one with the Jacobi's these, well, we do this number 1, number 2. So, well, in this case for x, it's not going to make much difference, but it's going to make much difference when we differentiate with respect to one variable and then we differentiate with respect with another variable. In this case, let's do the example in xy. So for example, we do the derivative with respect x, that's number 1, and then number 2 we do the derivative with respect y. Using the f notation, the subscript notation, we see the letter x and y in this direction. What I'm trying to say is, if we use the f notation, the order of the differentiation is from left to right. If we use the Jacobian notation, we go from right to left. So we do the partial derivative with respect to y first, then x. Do you see the subscript? We do the y first and then the x. Over here, we do the x first and then the y. Here, x and then y. So it's reversed. So when we go about these examples, I will use both notations just so we can, just to make sure that we get all used to both notations. All right. Okay. So find all second partials. All second partial derivatives for the function f of x y equals to 3xy squared minus 2y plus 5x squared y squared. All right.
What is that blank right there?
Hmm?
The last two second partial are known as.
Oh yeah, those last two. Oh yeah, it's very, very important. I almost forgot about this. Thank you. These two are known as mixed partials. And you will see what about them. We will notice a very interesting pattern about this. So number 1, let's find all second partials for this given function. So let's do partial f with respect x. Okay, with respect x, the derivative of 3xy squared, that's just 3y squared, and minus the derivative of 2y with respect x, 0. Okay, the derivative of 5x squared y squared, we're only differentiating the x squared. Everything else is constant multiple. That's 2 times 5, 10x y squared. Agree? All right. So let's find the partial derivative with respect y. Everything else remains constant. Okay, so the derivative of y squared, so that's 2y, so 2 times 3, that's a 6xy. The derivative of negative 2y, is that going to be 0 again? No, that's a negative 2. And the derivative of y squared, again, that's 10x squared y. All right? Okay, so let's have a look at the second partial differentiation. So this is what we're going to do. We are going to take the derivative with respect x of the already differentiated with respect x. So that is, we're going to do the second partial of f with respect x twice. All right, well, the derivative of this first term is 0. The derivative of 10x y squared, what's that derivative? 10y squared. 10y squared. Because the derivative of x is just 1. Everything else times the constant, that's just 10y squared. Let's do the second derivative with respect to y for the function, for the derivative that we already did with respect y. This means we're doing the second derivative of f with respect y. And well, okay, what's the derivative of 6xy? 6x, derivative of negative 2, that's 0, derivative of 10x squared y, 10x squared. All right? The next one. So, we are going to take the derivative. So, we already have the derivative of the function with respect to x. So, now we're going to take the second derivative, the second partial derivative, but this time with respect y. All right? So, we're going to focus on this first derivative with respect to x, right here, the one at the top corner, and differentiate this not with respect to x again, but we're going to differentiate it with respect to y. Okay, the derivative of 3y squared is 6y, and the derivative of 10x squared, yes, yeah, the derivative of 10x squared, 10xy squared, 20xy. Okay. Now, let's do something similar with the derivative of f with respect y, but this time we're going to take the derivative of, rather with respect x. Alright, so this quantity right here in the second column, 6xy minus 2 plus 10x squared y, we're going to differentiate it with respect to x. Okay, the derivative of 6xy with respect to x. 6y, the derivative of negative 2, that's 0, the derivative of 10x squared y, 20xy. Did you notice anything interesting, anything fun? These two are equal, right? That's what we call the mixed partial, because it doesn't matter the order you follow to do this, you should get the same. Alright? And again, what did we do here? Let me just go with the notation. So this means second partial of f with first with respect x and second with respect y, which in the f notation, that's fxy. Alright? We do the x first, with respect x, and then with respect y. In the Jacobian notation, we go with respect x first, and then respect y in the opposite direction. We write it down. Over here, second partial of f. Careful, we don't do with respect x first and then with respect y. No, we recall that we did with respect y first and then with respect x. Okay? I will be using both notations again for all of this. And well, so we can summarize the last result that whenever we have a function x of x and y, a function of x and y in such that the two partial derivatives with respect to y, then x, and then respect y, and if they are all defined on an open disk, well, notice the language here, how it's going to change. Back in Calc 1, we talk about functions defined in the interval a to b, right? Because that was just a segment, a line, or real numbers. In this case, because these are functions of two variables, the input is a point, it's an order pair, it's a projection of or like a circular, no, not circular, like a level curve, and then the height was the value of c. So in this case, it's defined for both x and y. So for every point, that's the result. That the mixed partial, the partial with respect to y and then with respect to x, is equal to the partial derivative with respect to y first and then with respect to x. So that's the result. That's the interesting result that we got in right here, in which we got the same result. All right? Yes.
Just about the previous definition from earlier. It says if w equals f x y z, that's a function of 4 dimensions. Should it be if z equals f x y?
I think that should have been only f of x y for now. Thank you. Thank you.